Hello AP Statistics students. In this video, we're going to take a look at what it takes to set your margin of error. Oftentimes, you want to set your margin of error before you do a sample and before you do statistics, because how terrible would it be if you did all this work to take a sample, to do a confidence interval, to do all that, and at the end of the day, your margin of error was like plus or minus 20%. Well, your data is worthless, and that's too big of a margin of error to have it be swinging 20%. Your numbers wouldn't mean anything. So oftentimes we want to set the margin of error, or at least predict where it might be beforehand, and then take steps to keep that as small as possible. Now, how do we do that? Well, there's only two ways to affect your margin of error, which we've talked about. You can lower your confidence, which is bad, or you can raise your sample size, which can be more expensive, but it's oftentimes your only option if you want your numbers to be believable at the end. So that's what we are going to do. We are going to pick our sample size and make sure it is big enough to lower the margin of error to an acceptable size. Okay, and so we're going to calculate those sample sizes that guarantee our margin of error. So let's take a look at how we do this. It's a bit algebra intensive, I'll warn you, but it's not that bad. So a company has received complaints about its customer service. The managers intend to hire a consultant to carry out a survey of customers. Before contacting the consultant, the company president wants some idea of the sample size that she will be required to pay for, right? It's expensive. How big a one do we need? One value of interest is the proportion, P, of customers who are satisfied. All right, there's our context, right? Satisfied with the company's service. She decides that she wants the estimate to be within 3 percentage points. All right, so there is our margin of error, plus or minus 3%. We want to be within 3 percentage points at a 95% confidence level. How large of a sample is needed? All right, so let's go to our confidence interval equation. Remember, the process here is you take your sample and you get your sample proportion. But you know that's not quite perfect because of sample variability. So you have to add and subtract the margin of error. Now, what is the margin of error? Well, that's p hat plus or minus z star, the critical value, times the standard error. All right, let's start filling in our equation. Now, we don't know what p hat is, right? We don't know what that is. But we're not actually interested in the p hat on that side because we're just interested in the margin of error, this part, right? We want to make sure that this part is less than or equal to 3%. So what is that part of the equation? Well, the z star comes from the 95% confidence level. So that is 1.96 times, what's the standard error? So the formula for the standard error is the square root of p hat times q hat divided by the sample size. There is the variable we are trying to solve for, right? This, oh, that was a terrible color choice there, Bolt. Let's not do that again. Is that better? That's better. No, it's not. That is the number or the letter we are trying to solve for in the end, right? And so I'm going to break that out. I want this whole piece right here. This is the part that has to be less than or equal to 3%. So let's write that down. 1.96 times the square root of p hat times q hat divided by n. All right, that's our margin of error. That whole thing has to be less than or equal to 3%. All right, so now it comes a little bit of logic. Because you're like, all right, I want to plug some stuff in so I can solve for n. Well, we got a problem there, don't we? We don't know what p hat or q hat are. How do I know what p hat is? That's the sample proportion. I haven't taken a sample yet. How am I going to know what p hat is? Well, a couple of things we can do. All right, couple of options. Option number one. Maybe you have an idea of what p hat. I think I got it. Whoa, whoa, whoa. Why did I jump way over there? Maybe we have an idea of what p hat should be. If you do have an idea of what p hat should be, use it. Now, how the heck would you know that? Well, maybe you had a practice sample that you did, an exploratory sample a smaller version, just to sort of test the waters. That is oftentimes done to test for bias questions or other stuff like that. You could then use that proportion. Maybe you've done a survey like this before in the past. Then you would have an idea what p hat might be in this new survey. But if you don't have any idea of what p hat should be, then you have to use the safest number possible, all right? You've got to practice safe statistics. I've been teaching freshmen since day one, practice safe statistics, okay? What's the safest number here? 50%, okay? 50% is what will make that value p times q the biggest, okay? Remember, that's our margin of error. And while, yes, we want to minimize it, so we have to pick what will make it the biggest. All right, we're going to make this part in the top the biggest it can be. And then we're going to force n to shrink it back down under 3%. Okay, just to show you that math, if p is 50%, q is also 50%, right? And 50% times 50% is 0.25. And just to show you, if you tip the scales, say do a 70%, which means q would be 30%. I can't do that one in my head. 0.7 times 0.3. That number is only 0.21. That's a little bit smaller. Okay? So if p gets swung either way, that number actually gets smaller. So this is the worst case scenario that would make our margin of error the biggest. So to be safe, we just use 0.5 as our possible p hat. Okay? So what happens to this equation? Let's do some algebra. So 1.96 times the square root. In the top, we're going to have 0.50 times 0.50 divided by the sample size. Hey, look at that. We now have an algebra equation with only one variable, which means we can solve this. So just sit back with me and let's solve this equation. This is like some of the most complicated algebra we ever do. To get n by itself, well, first let's get rid of the 1.96. We can divide both sides by 1.96, right? That will go away. So we're going to be left with the square root of, oh, let's do the middle. What's 0.5 times 0.5? 0.25 over n is equal to, not equal to Bolt, come on now, less than or equal to alligators matter. 0.03 divided by 1.96 gives us 0.0153. 0.0153. You probably want to use quite a few decimals here in the middle steps, so that way your round off error doesn't compound throughout the whole problem. So you want to use quite a few decimals here. All right, let's see. Well, we want to get n by itself, so we got to square both sides there, don't we? Get rid of the square root. Well, why did I cross it out on the other side? It's been a long time since I've done algebra. You too, huh? All right, so now if we want to keep your answer as accurate as possible, don't type in 0.0153, just hit the squared button here. That will use all the decimals. All right, so that gives me a big or a very small number, doesn't it? 0.0002347. I don't really like that, but 0.000, is that enough zeros? 23. Four, 2, 7, 2, 3, 4, 2, 7. All right, yeah, there's maybe a better way of doing that algebraically, but I did it, so I'm going to go with it. So that becomes 0.25 on the top divided by n. All right, so we got to get n by itself. Now, the alligator symbol means I'd highly recommend you show all your work and don't do any cross-multiplying stuff, because then you're like, wait, what side of the alligator symbol does it go on if I cross-multiply? Just show your work. Multiply by n on both sides. The n goes away. You're left with 0.25 is less than or equal to 0.00023 n. I'm going to divide both sides by that number now, right? Divide both sides by 0.00023. That goes away. You're left with n has to be bigger than or equal to this. Now, to keep my numbers precise, I'm going to type this into the calculator, but I'm not going to actually type in that big decimal number. I'm going to go 0.25 divided by second answer. All right, there's every calculator has an answer button, ANS, usually towards the bottom right. That way it will use all the decimal points for me, okay? And so even though I didn't write out all the decimal points in my work, my calculator keeps all of them so I don't have a round off error. So that becomes 1,067. No decimals here because these are actual people. You can't have decimal people. All right, so if we are going to do this survey and we want to keep our margin of error less than 3%, all right, we need to have a sample size of at least 1,067 people. So now we're good to do our survey. We know how many people we need so that our results are as accurate or as precise as we want them to be. All right, let's do that one more time. It's kind of a long process, but same problem, but this time we're going to have an idea of what p hat might have been. So the same company has a store 2 towns over. They had this same problem 3 years ago and completed a very familiar study. I think I meant similar study, not familiar. In their study, they had a sample proportion of p hat is equal to 0.32, so 32%. If we believe these 2 stores are similar in how they treat customers, how large of a sample would we need to keep our margin of error less than 3%? Still at a 95% confidence, though. All right, well now I have an idea of what p hat might be, okay? I've done this statistical analysis before we got 32%. I have some reason to believe this one might be similar, so I'm going to use 32% as my possible p hat when I calculate the margin of error. So remember, so our margin of error, I'll try to simplify this a little bit, is equal to the z star times the standard error, right? So my z star is still 1.96. My standard error is the square root of p times q. Well, I'm going to use this new p hat that I think might be close to what I get. So 0.32 times 0.68 then, right? Yeah, divided by n. All right, so I'm playing a little bit dangerous with the stats here. I'm not playing the safest option. The safest option would have been 50-50. All right, 0.5, 0.5. But I think this might be the proportion, so I'm going to use this one instead. And I still want that to be less than or equal to 0.03, 3%. I flipped the alligator sign because my equation's flipped around. Hope that doesn't throw you off too much. So I'm going to shorten the steps a little bit, do some things in my head. First, I'm going to divide by 1.96, right? So 0.03 divided by 1.96. 0.0153. All right, here I'm going to multiply the top. What is 0.32 times 0.68? 0.217. All right, I'm actually going to do a little fancy algebra here. I'm going to break up that square root. It's the square root of a fraction, which means I can take the square root of the top and the square root of the bottom, right? And so I think right now I'm just going to multiply by the square root of n to both sides. Multiply by the square root of n to both sides. That gets rid of that. And then I'll have the square root of n. Can I do another step in my head? The more you can shorten this algebra, the better. I mean, I've got the square root of n on this side. How am I going to get rid of this number? I'm going to divide it to both sides, right? So it's in your head, I divide it to both sides. Again, the more algebra you can do in your head, the shorter this process will go. So I divided it to the other side. And you can just type this whole thing into your calculator, I suppose, although you might want to be careful with how you do that. I'm going to do it in steps. So the square root of 0.217, but it's that number right there. So second answer, square root it. But then I'm going to divide it by 0.0153. So 0.0153, I'm going to add a 0.6. I can still see that number up here on my calculator. Hit enter. All right, so now that's what the right side of the equation is equal to. What's my last step? I need to get rid of the square root. So I'm going to square both sides. So if I square both sides, n will be greater than or equal to, square the other side of the equation, 928.8. So maybe round that up to 929. Again, we have to have an integer here. As you can see, that n value is now a bit smaller. Okay? We weren't playing as safe with the stats, but we're justifying that because we have an idea of what the sample size might be. Or sorry, we have an idea of what the p-hat might be. So, if you have to play super safe, you'll definitely get a number that works. But of course, the higher the n is, the more expensive it is. So while you want to have enough to minimize your your margin of error, you don't want to do it just a huge number. That's extra money. So if you have an idea of what the p-hat might be, you can still get your correct margin of error, but spend less money on your sample because it's not bigger than it needs to be. Now, of course, if you then did this study and your p-hat was way off of 0.32, well, then you kind of got screwed because your margin of error will then be bigger possibly, but hopefully not that bad because you are basing this smaller sample size off of this hypothesis for what your p-hat might be. But the math is the same, all right? So just the algebraic steps you need to get n by itself from this. All right, that's how you set your sample size. One more thing I want to do with my few minutes left here. I would be remiss if I didn't show you how to do a confidence interval on the calculator. Yes, your calculator can do a confidence interval for you. I want to show you that real quick, okay? So we got our old, we've done this problem like a million times, right? The cell phone, walking into things. We've all done it, but we won't admit it. Well, maybe some people will. We're doing a 95% confidence interval here, okay? Our sample size is 738, and 170 people admitted to it. So let's do a 95% confidence interval. Now, yes, we've checked all the 4 steps before, so I'm not going to do that. I just want to show you real quick how to do this on your calculator. So for a TI-84, you go stat, tests, okay? And then you have to scroll down. Hopefully some of these might sound familiar, like pretty good. We want a, there it is, 1 proportion Z interval. We've written that before, haven't we? 1 proportion Z interval. It's a 1 sample Z interval for proportions. So you hit enter. And so the things you have to type in, first, the X right here is the number of successes. We have 170. All right, it's not a proportion, it's not a percent, it's the actual number of successes. The sample size, in this case, is 738. That's what N is. Confidence level, we want a 95% confidence level. It will do all the calculations for you. Calculate. There it is. So, 0.199999, well, that's 20%, isn't it? It rounds up, 20%. And then this is 26%. We have our confidence interval. Hopefully those numbers look fairly familiar. We've done them a couple of times. But the calculator can give it to you right there. So again, you go stat, test, scroll down. I think it's letter A or letter B. A. It's letter A. 1 proportion Z interval. You type in the number of successes, the sample size, the confidence level, and you calculate. All right, if you have the Casio, it's very, very similar. Okay, you go menu, stats, of course. Only the first button. It's not under test like it is for the 84. It's under right here. I think this stands for interval. All right, INTR, interval. F4. You want a Z interval because it's off Z stars. You want a 1 proportion. Yes, we will do all 4 of these. We're going to do a 2 proportion here in the next couple of days. F5. And then it asks for the same thing in different order. The confidence level, 95%. The number of successes, 170. And the sample size, 738. Hit enter, and there you get your confidence interval from about 20% to 26% is our confidence interval. All right, one more of those real quick before I let you go. So in March, this is another question we did on the Desmos a little while ago. In a March 2016 survey by Gallup, 1,019 adults, that's our sample size, 65% believe that global warming is due to more to human activity than natural changes, create a 95% confidence interval. Well, we got the sample size, but we don't have the number of successes, and that's what our calculator needs. Not the 65%, but the number of successes. So you simply have to do 65% of the sample size. All right, that will tell you how many people actually said, I think, more to human activity. So you have to turn the percent back into the number of success. N times P, right? We've done that many times. So get out of here, 0.65 times 1,019. So this is a little round off error. You can't have 0.35 people. So 662 is what we're going to use here. So now when I go stat, tests, 1 proportion Z interval. All right, it was 662 successes, right? My N was 1019. Calculate. And there it gives us our interval from 62% to 67.8%. Maybe even 0.9%, huh? That rounds up quite a bit. Hopefully those numbers sound familiar to you. To show you them on the Casio one more time, you go interval Z, 1 proportion. Let's see, our successes was 662. Our sample size was 1019. And there we have our interval, the lower and the upper for the confidence interval. It even lets you, they both give you p-hat, right? So you can check to see if you entered that in right. Our p-hat was 65%. This one's 64.96. That rounds up to 65%. All right, hopefully that makes your life a little bit easier, that your calculator can do a confidence interval for you to check your math. Have a good one, everybody.